Welcome back to our last session of the day on the climate action stage. In this session, we'll be showcasing some AI in action. First up, Rothhamsted Research Centre. The institution focuses on strategic agricultural science to the benefit of farmers and society worldwide, and is the oldest continually operating agricultural research station in the world. Despite this, they are leading the way in the future of agriculture. Over the next 30 minutes, we'll hear all about Rothhamsted Research Centre, followed by a live Q&A, so please do send in your questions using Slido. But first, let's hear directly from them about their work.
Here is a study that uses artificial neural networks for the purpose of monitoring network optimization. This is a practical example that builds on the data of a national insect survey. The suction trap network began operating in 1964. Each unit continually samples the air column, sucking in some small to medium-sized insects. At its base, aphids are drawn into a sample bottle filled with preservatives. Samples are collected daily during the aphid season. The map on the right shows the location of all the current and historical traps. The catch is then taken into a lab and identified by a dedicated team of aphidologists. There are 600 species of aphids in the UK, and we catch 400 of them, including all the species that pose a threat to agriculture. The aphid data is then sent to insectsurvey.com to inform farmers of the likely season ahead. One key piece of information is the season start, measured as the first flight, because this alerts farmers to inspect their crops. To understand and predict aphid dynamics better, we will always need more traps, but those are costly. So the question is, were we to add a trap, where should we put it? Here we are interested in the arrival of 14 species of aphids, most of which are pests. So you see here on the right a measure of how late they arrive within a season, the day of 1% detection. And it is shown for all traps since 1964. So where should we add a trap to predict that specific event better? We will use this dataset to train a model at predicting aphid arrival and be guided by the uncertainty of our predictive model. The model predicting the arrival of 14 aphid species, it is therefore a multi-output model. As input, it uses environmental predictors derived from weather and land cover maps. Then we estimate the uncertainty of the model prediction, building on two techniques. First, a quantile loss functions that will allow the estimation of aleatory uncertainty, and then an ensembling approach to estimate the epistemic uncertainty. The uncertainty marks where additional traps would help filling a knowledge gap. Coupling this information with the density of crops at risk of infestation, we identify several locations in which predictions are unreliable and mispredicting an infestation could be costly. Such locations are ideal candidates for setting new traps. A trap was therefore added in location B2 in the Vale of York, where crops are very abundant and where aphid migrations are poorly captured by the neighboring trap. Thank you for your attention.
Okay, so I'm Sam Cook from Rothhamsted Research, and I'm going to be presenting about AI pollen beetle detection with Dr. Emily Bick from the University of Copenhagen and Fauna Photonics. So I'm standing in a field of oilseed rape. Oilseed rape is used for biofuels and for cooking oil and for animal feed. It's a really important crop, but unfortunately it is attacked by a very small insect called the pollen beetle. The pollen beetle invades the crop at this time of year. It eats through the buds of the plant, so they fall off and we don't get any pods and no yield. So in order to protect the crop from the pollen beetle, farmers have to spray it with insecticides. In order to know whether or not to spray the crop, farmers have to walk a transect all the way into the middle of the field, every 10 meters or so, taking a plant, beating it into the palm of their hand and counting the number of pollen beetles that they find. if the number of beetles per plant exceeds 15, then farmers should spray. But unfortunately, this technique is labour intensive and it's also rather inaccurate because pollen beetles aren't uniformly distributed across the field. They occur in hot spots. So depending on where farmers sample, they might get an inflated or a reduced number compared to the full value of the crop. So to help farmers to more accurately identify where the beetles are and how many they are, we decided that we needed to improve detection methods. So Rothhamsted Research teamed up with Fauna Photonics from Denmark to develop an automatic identification tool. So to solve the threshold problem and the automatic detection of pollen beetles in Aussie grape fields, we started off our project using LiDAR, which is light detection and ranging, basically a big laser, which was a massive piece of equipment and it took up a whole shed, as you can see here in the picture. But the LiDAR shot a beam across the field, and this beam was extremely powerful, ranged over a kilometre in length. But we were able to show that pollen beetles flying through the beam correlated with the number of insects that we found in the traps. So we were very pleased with this. And as the season progressed and the project progressed, the equipment basically got smaller. So here you see the long range detection equipment, which was around 1 metre in length. That was the next season. And then the season after that, we now find ourselves using a shoebox sized piece of equipment, which is the Fauna Photonics Veetle machinery.
So this is Fauna Photonics' Veetle sensor. How it works is it has a panel of LEDs that shine out light to illuminate an air volume about 0.5 meter in front of the sensor. Now, whenever an insect flies through that air volume, the light that's shown out of these LEDs gets backscattered off the insect and collected in a panel of photodiodes. Now, when the insect's wings are out, when it's flying, we see more light illuminated. And when the insect's wings are down, at the bottom of a wing beat, we see less signal back. So from that, we can start to tell what the wing beat frequency of an insect is. We can also say what's the body to wing ratio of that insect, as well as how dark the insect is based off of the relative absorption from the 2 different wavelengths coming out of these LED panels. However, it's much easier to identify an insect when you put these insects and have them fly in front of the sensor, a known number of insects, a known species, and you then can train a machine learning algorithm on exactly that signal. And thus, using that algorithm, we can tell what is actually flying in front of the sensor.
In order to provide algorithms that could automatically identify insects, we collected insects from the field, we identified them taxonomically, and flew them through the beam thousands of times. This enabled us to get many records of the flight behaviours of pollen beetles. And here you can see what a pollen beetle looks like through the sensor. The spikes are the wing beats, and the different colours show the channels, which are 2 different wavelengths and 4 different diodes.
We use a machine learning algorithm to classify signal as pollen beetles. Specifically, we take 10,000 events and separate those flights into 3 different categories: validation, training, and test sets. We train the convolutional neural network with that training set data, testing it at the end of each against the validation set, and back propagating the data through the network. At the end of the epochs, we test the convolutional neural network against its test set. However, we'd like to actually test this strategy in the field. So we set 6 sensors in a field, 30 meters from the edge, 45 meters apart in 2 transects, watching the immigration of pollen beetles into a field. On top of that, we laid 25 green water traps in a grid formation. And every single day when we went out and emptied those water traps, we placed 450 plants, which we beat on that grid area as well. However, we would expect that the sensors, the water traps, and the plants actually detect insects differently and monitor insects differently. As the sensors see insects flying over the plant, the green water traps see the very first landing spot in that field And when we beat plants, we're getting a real density of insects in that field. So when we look at the results, we're actually going to see the sensors light up sooner before the plant counts. And here we see the sensors in green and white light up. And then we start to see, as the plant counts start to get insects, start to see dark blue light up over there. And you can see there's both a time and a space difference here. So specifically, we see a couple different things from this case study. First, we can tell that the sensors see insects 5 days ahead of the plant counts and 3 days ahead of the water traps. We can also tell that we're getting over 2 orders of magnitude more insects through the sensors than through each water trap and through the plant counts. And additionally, where the sensors see the greatest number of insects is not actually where we see them in the field. So it's loosely correlated. These sensor counts are loosely correlated with the water traps, but not the plant counts. So in conclusion, we have shown that an AI can actually detect pollen beetles. And this type of technology can be used as an early automatic detection of insect species in real time. Moreover, a network of this type of sensor can be used to interpolate insect trends across landscapes. And technology and AI methods are widely applicable to many agricultural systems. Thank you.
Wow, some really fascinating applications of AI technology there. Now, it's my pleasure to introduce Chris Rawlings, who is Head of Computational and Analytical Science at Rothhamsted Research. And he's joining us virtually, and he's here to answer any of your questions if you want to put them through Slido. So hi, Chris.
Hi, thanks very much for inviting me on.
Good to see you there.
Obviously, you only saw a small sample of the applications of AI that we do at Rothhamsted, but hopefully they were illustrative to the audience of the sort of things we've been interested in recent years.
Well, I'd actually love to hear more about other case studies that are really interesting to you. Can you tell us more about the kinds of research that's going on?
Yeah, I mean, some of our work is around the use of other imaging-based technologies where we use approaches to measure plant development. So we have another area where we're phenotyping plants in the field and in the laboratory for their ability to grow under different conditions, or their ability to provide high resolution data on the dynamics of plant growth and the timing of specific plant development events. And that can help us understand the genetics that underlies the control of plant growth and plant development, which can then in turn help us understand better the mechanisms that we need to inform our colleagues in the breeding industry to how they should be selecting crops and selecting plants that are more likely to be, say, resilient for climate change events. And those might be heat or drought in particular.
There's such a diverse array of research projects going on under the umbrella of AI, but how did the actual idea of the Rothhamsted Research Centre come about?
So I mean, as you mentioned in the introduction, Rothhamsted has been around for a long time. We're a very old research institute, and of course, as we've evolved over time to adapt to the availability of new technologies. And what's transforming the way we do our research now is the emergence of affordable sampling and imaging technology that we can deploy at all sorts of scales. So the two examples you saw in the video clips, one is about a national network of sensors that are sampling the atmosphere for the appearance of insects that might be carrying plant disease. And on the other, you saw a much more local application of a related technology where we're using an imaging approach again to detect specific crop pests. In this case, it was cabbage stem flea beetle on oilseed rape. But it's the combination of many more sources of digital data in farming. And that goes from the big farm instruments like tractors, where they have lots of information about the way in which the tractor is being used or about the crop that it's harvesting. And that information can flow through to our scientists and look in a lot more detail to identify particular problems in the data or to extract particular types of information from the data. Some of that uses AI, not all of it, but increasingly we see opportunities for AI methods to help us make good decisions or improve the quality of decisions that were previously made by humans at a much more costly and time-consuming way. And we're at the beginning of this journey. We're at the beginning of this journey, I have to say. So, you know, we can see many more opportunities than we've been able to make any practical applications on.
And as the technology develops and the research continues, how do you see your focus of research evolving?
Well, I think predominantly we will have to deploy many more people whose task is to integrate and quality control the data that we gather. At the moment, much of our data is very hard won. It's very expensive to collect. We have to do very large scale experiments in fields, which take a long time. You know, the growth of a crop happens once a year in the UK. And I think we can see opportunities for sort of improving the efficiency of our research and getting more information out of the data that we collect, so that we can be more helpful to people and we can more rapidly apply the methods that we develop using AI or other data science techniques and deploy that to farmers more directly than we can do currently.
So we've got a couple of questions from the audience. The first one is, how can we ensure that this technology is affordable for farmers in lower and middle income countries, given the cost of some types of monitoring stations?
I think we have to, you know, I think the example on the insect monitoring case study that Sam Cook and Emily presented shows that as you develop the research, inevitably the cost of the instrumentation drops. And we have examples in our soil science area where we have expensive instruments in the lab, but now smartphones and slight modifications of smartphones enable us to consider that we could use some of the same spectral methods that we currently use on expensive instruments being deployed on a handheld device in the field. And there are people actively working on this, and we've been involved in some of those projects. So it's about, you know, demonstrating that the technology works in a laboratory environment, moving it out to the field, and then seeking the right type of sponsors which help you drive the costs down and deploy that to people in lower and middle income countries. But you have to show that it works first, right? You know, with the expensive kit before you can then validate that using cheaper alternatives.
Yes, and there seems to be a certain area of research that acknowledges that hardware can be expensive, and it's a case of developing the software to work on less expensive hardware. So there's so many different areas of research going on.
Yeah, and the other factor is that we currently in a research environment, we're collecting all the data that we can in as dense a way as we can to help identify the minimal amount of data that we need to make the decision. And then sometimes you're in a position to build a more precise instrument that actually measures what you need to measure, and you can deploy that more cheaply than when you've got a research instrument that can do everything with all the bells and whistles that you need in a laboratory.
Great point. The second question is, what's the next step for the insect pest detection technology? Is it leading towards minimizing pesticide use through intelligent spraying? I
think the particular interest at Rothhamsted is certainly in reduction of any use of chemicals, but that program is part of an active strategic area that we have at Rothhamsted of using beneficial insects to deliver ecosystem services, which can help prevent the use of spraying. And so, as well as monitoring pests in the field, the sensors potentially can be adapted to monitoring beneficial insects. And so there are many ways in which we can take this research forward, either by providing more extensive surveying for different types of pests, but also for ensuring that the good ecological practices that the farmer might undertake are actually being effective in the field. And that would be, the aim there would be to reduce the use of pesticides.
Another question is, how can we use AI with pollinating insects? I'll start again. How can using AI with pollinating insects contribute to reducing the decline of these species?
Well, I think this is probably a question for an ecologist rather than for a computer scientist. But I think ultimately a lot of the use of AI is about understanding insect behavior. And that is both about understanding the behavior of the insect in a normal environment and also in artificial environments. And we have done some work on that at Rothhamsted. But it's about the whole piece. It's not all about AI particularly. It's about understanding all of the dimensions, all of the data that comes from an ecosystem, and understanding the role of how farming impacts on that ecosystem, and also about the way in which insects behave under the influence of different stresses that are put on that ecosystem. And farming may be one of those stresses, but actually climate change can be another, or natural predators can be others. Fire, for example, I know some people are interested in other countries where bushfires and other things can also have a huge impact on the ecosystems that are in agriculture or in urban or in wild ecosystems. So there's no simple answer. I think it's really about using the right AI tools to help understand and better understand insect behavioral changes under different types of environmental stress.
There seems to be such an array of research that goes on within AI in agriculture. At Rothhamsted, do you try to stay focused in a particular area? And if so, what is that focus?
Even within an organization such as Rothhamsted, where we are focused on a number of different, a relatively small number of agricultural systems. And so the agricultural systems that we concentrate on are the arable ecosystems. And so that's the arable rotation involved largely in wheat production, but potentially also in other broadacre crops, such as oilseed rape that you saw in Sam Cook's presentation, but also to a certain extent in sugar beet as well, where there are other problems with insect pests that bring virus into the crop. So basically the wide area crops we look at in the whole, but we also look very closely at pasture-fed meat production at our Devon site in North Wick, and there we have a research platform which is designed to capture high-resolution data on the entire farming system, and that's everything from the very beginning and how the grass is grown and what in the pasture and what types of grass is grown, right through to the quality of the meat that's produced at the end. And so we have a complete beginning to end process in terms of a meat production ecosystem that is very important in the west of England. We don't, for example, look at dairy. We don't look at horticulture. We don't look at high intensity methods such as vertical farming. I mean, other people are doing that, but we have a particular remit from our funders, the BBSRC, a part of UKRI, to concentrate on those areas.
So Chris, are you able to say something about the hardware requirements, like supercomputers, desktops, phones, that you use for your AI methods?
Most of our methods use fairly straightforward multi-use Unix clusters. We don't currently use a large amount of hardware for the learning tasks that we have in hand. And so we predominantly use sort of either big desktop environments or a high, a medium performance computing Unix-based cluster. No fancy kit yet, but I think we are aware as we move to more and more of these applications, we may need to invest in some of that or find access to that.
It will be really interesting to see in the future how the advancement of computing technology coincides with your research, because it will have a significant impact, won't it?
Yeah, I think in terms of our compute capacity at the moment, it's not a rate limiting step. I think if anything, it's the amount of label data that we can use to train and validate our methods, and bringing in data from lots of different sources with equivalent quality, so that we can be confident of the applications and the algorithms that we employ. So it's going to be the volume of data and the density of the data that and the velocity of the data that's going to have the biggest impact, I think, on whether we need to move to some bespoke hardware platforms for doing some of the deep learning methods, for example, which might become more relevant.
Well, Chris, thank you so much for joining me today. It's been fascinating to see a few slices of the research that's going on at Rothhamsted, and I look forward to seeing more in the future. Thank you.
Yeah, well, hopefully we can come back next year and give a bigger showing, and you'll learn a lot more about what we've been up to. But thanks very much for the opportunity today.
And that's it for Climate Action today at AI UK. Make sure you're back here tomorrow for more research talks exploring energy and the link between our health and climate and the use of climate data in art and public engagement.